In the last video, I have explained you Rutherford atomic model, observations and conclusions. Now, as per the conclusion, we know that nucleus is having a positive charge and that is at the center of an atom, and that carries the entire mass of an atom. Okay. Now, let me redraw the alpha particle scattering experiment here, but only the alpha particles approaching the positive charge nucleus. So, alpha particles which are going very far away from the nucleus, that will be undeviated. Okay. Now, when the alpha particles are coming nearer, going nearer through the positive charge nucleus, that will be deviated by an angle of 1 degree, more than 1 degree. It's not 1 degree, more than 1 degree, theta more than 1 degree. When it is very close, what will happen? That will deviate by an angle more than 90 degree. So let me redraw it on this side as well. Undeviated. Now very close, what will happen? So before that, in between, when it is closer to nucleus, that will deviate by an angle of theta more than 1 degree. Now it is very close, theta greater than 90 degree. Now here with this experiment, we will learn two parameters. One is impact parameter and other one distance of closest approach. This one is very simple and this one I'll explain it to you. Now impact parameters is nothing but the perpendicular distance between direction of approach the alpha particle is making and with the center of nucleus. Now what is that? What is the direction of approach? That is nothing but the direction of initial velocity. Why we are talking about initial velocity? Now that this alpha particle has an initial velocity in this direction. Now once it reaches here, then the direction of velocity changes. Magnitude may not be changing, but the direction has got changed. Now here in this case, to get the value of impact parameter, you should be considering the value of initial velocity, basically the direction of initial velocity. This one is the initial direction of initial velocity. So let me complete the direction. Or I could also take it as direction of approach. This one is the direction of approach. It is approaching in this direction. Now this alpha particle is approaching in this direction. Now that is also equal to the direction of initial velocity. This one is the direction of initial velocity and that one is the direction of approach. Initial velocity, direction of approach. Initial velocity, same thing. Either you can say direction of initial velocity or you can say direction of approach. Both are the same. Now with this line, just find the perpendicular distance with the nucleus. This one with this alpha particle, this is the impact parameter. Now with this alpha particle, this one is the impact parameter. Now with this alpha particle, this one is the impact parameter. Now with this alpha particle, from nucleus, take the perpendicular distance, impact parameter. From this, take the perpendicular distance. This one is the direction of approach. So this one is the impact parameter. So from where you have to take the measurement? From nucleus. Till where? With the direction of approach or with the direction of initial velocity. So this is very simple. Next one is distance of closest approach. Now there we are going to talk about the nucleus which are approaching, the alpha particles which are approaching the nucleus with a head-on collision. So this alpha particles will move all the way in this direction and at some point that will return back. So that is not exactly after the collision because it will not be able to collide here. Why? The alpha particles when it is here, the Coulomb's attractive force is, this is not attractive, repulsive force, because is 2 plus. Alpha particle is a helium nucleus. Helium nucleus has 2 positive charges, that is 2 protons. Now this proton will be repelled by the nucleus. But here when it is very far away from here, repulsive force is 0. Now when the alpha particle approaches in this direction, here let's say the alpha particle is, now the force is more. Now when the alpha particles comes here, force is more. Then the force keeps on increasing till a particular value. Till when let's say the alpha particle has got an energy of 100 joule, for example. Now as it comes here, basically this alpha particles has to do a work against this repulsive force. A positive charge is trying to repel to this positive charge is giving a force in this direction, right? But the alpha particle is coming in this direction, that is opposite to the force exerted by the nucleus. Now when it is going in this direction, it has to do a work. How? By using its own energy. Now this energy, the alpha particles, initially it is having certain energy. With that energy, that will approach the nucleus. So during that process, its velocity will decrease. Why? Because it is having initial energy in the form of kinetic energy. Now with this kinetic energy, it is doing work and going opposite to the force. What is the force? Repulsive force. Now as it moves, so this kinetic energy will decrease, which means this will gradually slows down, and here the velocity will become 0, and after that what will happen? It will return back. Now what will happen? It will use to do a work, the whole kinetic energy will be used. But according to energy conservation, we know that energy have to be conserved. So it can neither be created nor be destroyed. Now what will happen to this work done? That work done will be stored as potential energy. Which means when it moves from here, it has all the energy the alpha particles carry is in the form of kinetic energy. Now when it approaches alpha particles in this direction, the kinetic energy will get converted as potential energy. Now the value of kinetic energy will decrease. So what is the equation for kinetic energy? Half mv square. Now how can it decrease? Velocity will come to, will slow down or will reduce. So velocity, if it is 100, now that will become 90, then 80. In this way velocity will reduce, kinetic energy will reduce, at the same time potential energy will increase. Another example I will give you. So with that, this concept will be very clear. Now when we are throwing a ball upward with a 50 meter per second. Now the moment you throw the ball, it's with you, right? It's on the surface of earth, or the distance is very, very less. What is the distance? Approximately 1 meter. So we will take that, we will consider it as stone at the surface of earth, and that is trying to go upward with initial velocity of 50 meter per second. Now what energy it is having? Kinetic energy. What is that? Half into mass of the ball into velocity square, 50 square. Now as it moves upward, it has to do a work against the gravity. Gravity is trying to pull it downward. So what will happen? The velocity will gradually reduce, 40, then 30, and finally it will become 0. But what will happen to this initial kinetic energy? That will be stored as a potential energy here, mgh. Clear? So whenever it goes upward, here it is 0, h is equal to 0. When it goes upward, h value will increase. So when h value increases, mgh value will increase. Now when it goes upward, velocity will decrease, so kinetic energy will decrease. So total energy will always be conserved. What is that? Total energy is equal to kinetic energy plus potential energy. Now when kinetic energy decreases, potential energy will increase. So here in this case, alpha particles going in this direction, so it has to oppose the Coulomb's repulsive force. Now when it do so, the velocity will decrease. When velocity decreases, potential energy will increase. Now here, what will happen? All kinetic energy will be spent on potential energy. So everything has now got converted into potential energy. So we know the initial energy of alpha particle, that is 7.7 mega electron volt. With experiment we have calculated the value of alpha particles, that is the initial kinetic energy. Now using this we have to get the value of closest approach. What is that? Distance of closest approach is the minimum distance alpha particles of an alpha particle alpha particle that reaches just before it returns back. Now alpha particles goes in this direction and at certain distance that too comes back. Okay, so this is the minimum distance. Beyond this alpha particle cannot go. I'll repeat it. With this kinetic energy, it will come in this direction, along this direction. So kinetic energy will decrease, potential energy will increase. After some point, that will come back. Beyond this, it cannot go. That is, this distance is nothing but the distance of closest approach. Okay. Now, how can we get the value? We know the kinetic energy. Now, we have to equate the kinetic energy with the potential energy. Why? The whole kinetic energy has now spent on potential energy. We know the value of kinetic energy. What is that? 7.7 mega electron volt. Now kinetic energy is equal to, at this position, maybe the position is A and position is B. So kinetic energy at A is equal to potential energy at B. Now we know the equation to get the value of potential energy. Let's say alpha particle is a positive charge, right? It's not one positive, it is two positive. Helium nucleus, right? It has two protons. Now let's say this is an atom having Z atomic number. So atomic number is nothing but number of protons. Now in the case of gold it is 79. So let's say this is atom having Z protons, that is atomic number nucleus with an atomic number of Z. Now with that case it will have Z number of protons, because if the atomic number is Z, atomic number is nothing but number of protons. Now how many protons it is having? Z number of protons it is having. Now how much positive charge it is getting approached? That is 2 positive charge. That is charge of alpha particles. I'll repeat, charge of alpha particle is 2 positive. Now that is going to approach an atom having atomic number Z. So atomic number Z means Z number of protons. So if it is having Z number of protons, it is inside the nucleus and the total charge of nucleus will be Z number of positive charges. Okay, here in this case plus 2 number of positive charge. So plus 2 into E and here plus Z into E. So plus E is nothing but charge of a proton. Here it is 2 into plus E. Here it is Z into plus E. Okay. So plus 2E approaches plus ZE. Plus ZE. Write the equation here. Potential energy is equal to 1 by 4 pi epsilon 0 Q1 Q2 by R. This equation we have learned in chapter 2. So here we can substitute the value 1 by 4 pi epsilon 0. Q1, what is Q1? Charge of alpha particle, that is plus 2. E, 2 proton. Now Q2 is charge of nucleus of the atom having atomic number Z. What is that? ZE plus ZE divided by R. This is closest approach. So I will make it as D. Distance of closest approach. Now how can I get the value of D? D is nothing but I can take KE this side. So this is KE, right? Which will be 1 by 4 pi epsilon 0 2E into ZE divided by KE. Now substitute the value. This is 9 into 10 power 9, 2 into 1.6 into 10 power minus 19. Z, if this is gold foil, then Z will become 79. E is again 1.6 into 10 power minus 19 divided by kinetic energy. I have told you initial kinetic energy of incoming radiation 7.7 mega electron volt. So this value, after substituting, after doing the simplification, we will get as 3 into 10 power minus 14. So we will take into femtometer, that is 10 power minus 15. So it can be written as 30 into 10 power minus 15 meters or 30 femtometers. What does it mean? That the distance of closest approach is 30 into 10 power minus 15 or measured in 10 power minus 15 meter. Now this also gives the conclusion that the size of nucleus here in this case should be less than the distance of closest approach. So that is not conclusion from this. From Rutherford postulates, from Rutherford's conclusions, this distance, that is distance of closest approach, should be greater than the size of the nucleus. Or I can say that size of the nucleus, this one, should be less than this distance. Now what is the distance we got? 30 into 10 power minus 15 after substituting the values here in this equation. Now what should be the size of the nucleus? It should be less than this one. So if this is 30 femtometer, the value can be 20 femtometers or 1 femtometer. So I could say that 10 power minus 15 meters are the range on which the measurement of nucleus, size of the nucleus is made. Now if we are doing, with this concept, with this values, we can say that when we are taking a football stadium and considering the size of football as the size of nucleus, then the whole football stadium, including everything, is the size of an atom. The size of an atom considered as a football stadium, then size of the nucleus will be size of the football in that football ground. Okay, so that is the conclusion, that the size of the nucleus is very small and the size is measured in femtometers. That's all. So, thank you.